So good morning to everyone. My name is Michele Girolami. I work for a National Council of Research and in particular for ISTI Research Institute. This work is a collaboration between CNR and the University of Pisa, and in particular with Professor Stefano Chessa and Emanuele Erzelli. We present our work, which is entitled Encrypted Data Aggregation in Mobile Crowd-Sensing based on differential privacy. And in this work, we are going to analyze, to investigate the privacy problem for the mobile crowd-sensing paradigm. Let's start by reviewing the goal of the crowd-sensing paradigm, which is to collect and to build a representative dataset by exploiting the sensing capability of mobile devices. The idea is to exploit the sensing features of these devices in order to exploit them as a source of information. A crowd-sensing paradigm is composed by a number of volunteer users which decided to join a crowd-sensing experiment and to provide data. They are usually equipped with a mobile application in charge of receiving a task from the mobile crowd-sensing backend and to upload the data back to the mobile crowd-sensing backend. A task can be defined as an action to be performed with or without the explicit user intervention. For example, sensing temperature in a specific region, or collecting pictures from a square, or providing a feedback from the quality of services in a city, or for example from a public institution. We further analyze how data can be uploaded, and so we introduce the notion of data providers, which are the entities that uploaded data useful for the crowd-sensing initiative, for the crowd-sensing campaign. They do not upload plain data, rather they use cryptograms in order to encrypt the data. And these cryptograms are collected by the aggregators, which receives and combines such cryptograms in order to decode the aggregated version, but without being able to disclose the entities of the owners of the data. More specifically, what we want to address is the problem of assuming that if the aggregator is not reliable, it might, for example, misuse the data and possibly attempt attacks to infer additional information about the participants. This is a problem that exists also without the existence of an aggregator. So this in the middle entity which collects these cryptograms, because in a plain mobile crowd-sensing architecture, the data provided might be, for example, uploaded in clear text. So a man in the middle might sniff the data and disclose personal or sensitive information about the data providers. The goal of this work is to further make more robust the crowd-sensing architecture by introducing an aggregation mechanism. So data are aggregated in an encrypted form, and the aggregator is only available, can only decrypt the aggregated form, but without knowing the real entities of the owner. So before detailing our proposal, we rely on the solution provided by Chen et al., reported at the bottom of the slide, in which authors propose to split users in overlapping ring groups. Each ring is composed by a number of users, and each ring is assigned some secrets. In particular, each user calculates Ri, I plus or minus 1, which is the results of Q, which is a large prime number, and G, which is a group generator of the cyclic group G. The group manager generates a random variable as I, and so in this way, each users keep 3 secrets, which are Ri, I plus 1, Ri, I minus 1, and Si. And then each data provider can create the cryptograms CIT, which is composed by XIT plus RIT. XIT represents the collected data summed with a noise given by the difference between 2 gamma distributed random variables of a specific shape, for example, alpha. And the noise allows to introduce the noisy component so that the aggregator cannot disclose the owner of the data. RIT different is obtained by the cipher keys RI minus 1 and RI plus 1 used at time t by the device I, to encrypt the XIT part. And RIT is the results of the difference between two one-way hash function plus a pseudorandom function F. And the authors propose to use HMIC SHI 256 as a key as a pseudorandom function. So in this way, the aggregator receives a collection of cryptograms, one for each the different data providers. So the sum of CIT can be seen as the sum of the XIT components plus the sum of the RIT components. What we want to extend this mechanism by introducing a buffering mechanism which allows the aggregator, which allows to answer to the problem that the data providers can upload the data synchronously, and the data provided might be delayed or even lost. So the aggregation process should be tolerant to the missing information. To this purpose, what we have done is to introduce the buffering mechanism that allows the aggregator to fill the missing data in order to correctly calculate the aggregation. But this buffering mechanism might introduce two possible drawbacks. On one hand, data are replaced, and hence these are not real data taken from the slot. So this might alter the final result of the aggregation. And secondly, each data providers introduce some noise in order to obfuscate the real data. So we have two different sources of noise. What we have done is to exactly analyze the effect of the noise on the real data by using a simulation. In particular, we developed a simulator modeling the interaction in a CrowdSensing architecture. And we studied the effect of the noise and the loss of data in a CrowdSensing application implementing the encryption schema previously introduced. We considered some environmental data collected from the Weather Underground Service, which provide the real data about readings about temperature, humidity, and other environmental parameters from different cities in Italy, and we selected Bologna as reference city. And the stations, we collect the data from 10 different stations for a period with a sampling rate of 10 minutes for a period of 2 hours. And the data, what we have done is to first analyze a low reading, to compare the average obtained by real world versus the computed average with a low number of readings. In the figure, indeed, we report on the orange line the real average compared with respect to the computed average in blue line. And we computed this aggregation by using only 10 readings, so a very few number of readings. Then we extended the number of readings, so increasing the number of data that we can encrypt and send to the aggregator, moving from 80 to 120 readings respectively. And these are the two figures that we reported in this slide. We also increased the number of noise in order to understand if the increase in the noise added by the data providers, the average computed by the aggregator differs significantly from the average computed with real and clear data. And we observed that this difference is only bound between 0.02 Celsius degrees, which is a very interesting result, because even if we introduce a lot of noise, so we try to anonymize the data, then it is possible to have a real average which is always comparable to the real one. So in conclusion, what we have done is to introduce an encryption schema tailored on the mobile CrowdSensing paradigm with an extension of the buffering mechanism to cope with asynchronous data provisioning. Our experimental data are designed to assess the impact of the noisy data during the aggregation, giving rise to a framework able to support high noise, but without losing a lot of information. Thank you for your attention, and if you have any question, I'm happy to answer. Thank you.